It's my pleasure to introduce Elaine Shi, who, as many of you know, is one of the authors or co-authors of some of the most important recent work on Oblivious RAM, and has also gotten interested in private information retrieval. Has a bunch of cool results in that area too. And she's going to give us a survey of those two problems and recent progress on.
Okay, yeah, thank you so much for inviting me. I'm very excited to be here. I'll talk about how to access data privately. I'll also try to give like a real world perspective. So I'm actually going to start with some real life applications, why people really want ORAM and PIR in the real world. We'll start with like Signal. Signal actually has ORAM running at a large scale today for their private contact discovery. So what is private contact discovery? Let's say Shafi joins Signal and she wants to fetch her friend's records. So normally she would send her address book to Signal, right? But Signal's value proposition is privacy, so they don't really want to know your address book. And moreover, Shafi is like privacy aware, and her address book is top secret. There's a strawman solution, which is to encrypt everything. You encrypt your query, you encrypt the database, and suppose so TEE stands for Trusted Execution Environment. So I'm going to use the word TEE, enclave, secure processor. All of them are interchangeable. And the idea is you don't have to understand how it works, but essentially there's a hardware sandbox. And inside the sandbox, there's a key that can decrypt all the data, and the computation takes place inside. But any data that leaves this enclave, like including data at rest and data in transit, is going to be encrypted. Okay, so you may think this solution would solve this problem because, if Signal had this TEE on its servers, you wouldn't be able to see the data, not the queries. But actually, it is not the case, because even if everything is encrypted, you still have to go to your database, go and fetch the records you want, and the access patterns to the database leak exactly what you want to hide. Like in this case, just by looking at which records you are fetching, Signal can learn Shafi's friends. And I also want to mention, a lot of people, they tend to dismiss this as a side channel leakage. But if you think about it, this is really not a side channel leakage. It is direct leakage of the data you care about hiding. Like if you only encrypt it and you don't protect the access patterns, the encryption is of little use. Okay. So this is why Signal really care about it. I'll also give you a blockchain example why, in blockchains, people are really thinking about deploying ORAM and PIR. And the application is private order flow. I want to say there are different applications in blockchain. I'm going to give one of them. It's private order flow. So let me explain what order flow is, right? So today, what happens in blockchain, right? There's the consensus protocol, and then blocks keep getting added to the consensus protocol. And behind the scene, essentially, there's a block builder who's going to propose the next block that's going to be added to this linearly ordered lock. And then the users are going to submit their transactions to the block builder, and the block builder will basically pick among the pool of outstanding transactions and build the next block. So today, everything happens in the clear. And the drawback is, if this block builder can see what transactions people are submitting, it can easily front run and back run people's transactions. And if you do this in a careful manner, you can make risk-free profit. It's like arbitrage. And it turns out this is something that's quite dangerous. In fact, so that there's this empirical paper by Yang et al., and they show because of these front-running and back-running attacks, Ethereum is becoming really centralized. Like today, between 80 to 90% of the blocks are built by only 2 block builders. So if you think about cryptocurrency's value proposition is in the decentralization itself. And this is exactly the reason why Ethereum really cares about fixing this problem. Okay. So one way to mitigate this is to have private order flow. So imagine everything's going to be done in some kind of encrypted or secure computation. way, right? Like the transactions are encrypted when it's submitted to the block builder, and it's going to like build the next block using encrypted computation, like either using trusted hardware or using something like FHE or maybe secure computation. But the same problem happens because when you build a block, you need to execute these transactions. And as the transactions execute, they have to access data that live on the blockchain. And these access patterns are highly leaky. They leak exactly the information you care about hiding, like what kind of crypto assets you want to trade and who are your trading partners, right? So it's also really important here that you protect your access patterns. Okay, and then I'll also talk about, I have to have an AI application. We have to have AI in every talk. So large language model, privacy preserving LLM, right? So like you think about all the queries you send to ChatGPT, and these large language models, they use this core algorithm called Retrieval Augmented Generation, or RAG. And what it does is it's going to transform your query, and the transform query will be used to determine which locations in this large knowledge base to fetch entries from. And then it'll fetch these entries, like do some computation, compose an answer, and send it back to the user. And here, it's exactly the same problem. If you think about it, the locations that are accessed in this knowledge base leak precisely the nature of your query, right? It is very important to hide the access patterns. Okay, so these are the 3 applications I want to use to motivate this line of work. And the question we want to ask is, can we provably defeat access pattern leakage while still preserve efficiency? Or slightly more formally, we can think of ORAM and PIR as having a similar security definition, but now I'll talk about what the difference is, right? So the problem we have is, like, imagine there's a client and there's a server. The client is trusted, but the server is adversarial. The server is storing some database, and the database, it's possibly preprocessed. And then the client wants to access some address X, and then they engage in some kind of interactive protocol. And at the end of the protocol, the client can produce the answer. The security we want to guarantee is like analogous to encryption. Like it's kind of like we want to encrypt the access patterns. Or more formally, imagine we have 2 address sequences of the same length, X0 and X1. We want to guarantee that the server's view in this protocol, no matter whether the input is X0 or X1, should be indistinguishable. So I mean, when we actually write our papers, we have an adaptive version of this definition. For the purpose of this talk, I'm going to just use this simpler version. Okay. So there are 2 primitives that can be used to solve this problem, called ORAM and PIR. And they seem to be providing something very similar, but there's some fundamental differences. And one important difference is that ORAM allows per client state. Like you can imagine, for every client, the server will be storing some preprocessed database, right? Whereas for PIR, it's more like there's a global database, and you don't want the server to keep per client state. And for this reason, like ORAM is the more suitable primitive when you have an outsourcing scenario. Like every client is going to outsource its private database to the cloud, and it's going to access its private database. Whereas PIR is more suitable for the scenario where there's a public database, or maybe the database can be private, but it's a global database. And in this case, like it would be much more efficient if the server did not have to store per client. Like it did not have to make a separate copy of the database for each client. Like, if you think about it, like Google cannot make a copy of their entire database for every user they have, right? This would be prohibitively expensive.
Okay, so Signal implemented ORAM or PIR?
ORAM, and it's going to be on my next slide.
Oh, okay.
So another thing, there are also some other more subtle differences, because typically in ORAM, the server is passive. It's just like a storage. It doesn't need to do computation, whereas in PIR, typically we assume the server can do computation. But I think this is kind of like the most important difference. So in today's talk, actually, if you think about other motivating applications I mentioned, they are more in this scenario, like there's a global database. So this is the scenario we are going to focus on, but ORAM is still relevant, even if it seems like what we want is PIR. And why is this the case? So back to Tal's question. This is like the deployed solution today. So basically, Signal has it running at a large scale. Meta also has an implementation, and I think they are going to roll out something very soon, and their code is already open source. And we are also talking to like various blockchain stakeholders like Ethereum, Flashbots, WorldCoin, and they are also interested in getting something like this deployed. And the idea here is like, why is ORAM relevant when we have so many different clients? It's because they introduce TEE, a secure processor, and the secure processor is going to act as a global trusted client for every user. So somehow it kind of overcomes the multi-client problem by having the TEE act as a single client.
So the industry is very happy with the trusted hardware?
No, exactly. So this is why I want to talk about the other solutions. No one wants trusted hardware. Ideally, in the dream world, we should not have trusted hardware. So here are some possible ways to get rid of the trusted hardware. One is to implement the secure computer, not using trusted hardware, but using, let's say, 2PC or multi-party computation. So throughout the talk, I'm going to focus on 2PC, but everything I ask about 2PC, you can ask the same about MPC. Okay. So in this case, like, essentially, you can just think of this 2PC as a crypto secure computer, and then the database is like secret shared among the two parties. Another way to get rid of the trusted hardware is private information retrieval, of course. So you may ask, okay, why aren't people using these crypto solutions? And I think one reason, maybe this is also one reason that's maybe partly relevant to Yevgeny's question. So in a lot of these application scenarios, it's performance hungry. Like for instance, in the block building application, when we talk to these block builders, they care about even millisecond level delay. For projects like Signal, Ethereum, they really want to roll something out today. Like they cannot wait. And that's why they're settling for trusted hardware. Like if you think about it, Ethereum has actually, they have long held the strong position against trusted hardware. But even for Ethereum, like for instance, they're kind of realizing if we want something deployed today for large scale, maybe it's better to first use trusted hardware and then think about how to get these other solutions more practical, maybe for tomorrow. Yes, Yevgeny.
Like high level. So my understanding is ORAM is already practical, including both reads and writes kind of updates. PIR, I guess you talk about, my understanding is like for static databases, there are various practical enough trade-offs, but if the database really changes, is it true that it's like order of magnitude?
Yeah, you're also ahead of me. Yes, I think for PIR, if the database is updating really, so it depends on, so PIR, I think the landscape is a little bit complicated. The scheme I'm going to talk about is client preprocessing PIR. And for client preprocessing PIR, if your updates are much, much, much faster than queries, then the client has to pay a high cost to keep track of the updates. But if your updates are kind of just as frequent as the queries or less frequent than the queries, then maybe it's fine. So there are some challenges. It will be at the end of the talk, like for PIR.
For append only, for some applications, you might want append only PIR. Is there a difference, or appends are as hard as overrides?
I guess like, I think for client preprocessing PIR, really, I think the thing to check is whether the updates are faster than your queries or slower than the queries. That's the thing that matters to practicality. Okay. But anyway, I think that I'll maybe answer your question better towards the end of the talk. Yes.
For the TE-based solution, how do the clients check the attestations for the TE?
How does the client check the attestation?
It's encrypting his data and sending it to this enclave.
I think for Signal, it's not checking attestation. Like Signal is kind of like, you can assume the server is semi-honest and they don't want the accountability, but it's not hard to build the attestation in there. Like I think but we are also collaborating with Flashbots, and for like the demo we are building for Flashbots, like they want us to put the attestation in there, so we can do that. Okay, so I guess a lot of the previous talks, like you start from beginning of time. I'm going to do it in slightly reversed. I'm going to like first tell you where things are today, and then I will rewind and show you how we got to this point. Okay, so where are things today? For ORAM, this is the fastest implementation I'm aware of. It's by my company, Oblivious Labs. We can, like so the database in all of these tests are realistic sizes, like from 100 gigabytes to 1 TB. And the size is determined by like these applications we are talking to, like Ethereum, blockchain, Signal, so DNS database, right? So these are realistic data sizes. So every query can be supported in 20 to 50 microseconds. This is not even milliseconds, it's microsecond level. So it's extremely fast. And this, so everything's on a single machine. And I think, so this number is like, you don't need parallelism to get this performance. And if you have like a lot of queries coming in batch, we can get the throughput to 200K queries per second on a single machine. And if you have more queries, like ORAM is easily parallelizable. You can easily just introduce multiple machines and parallelize the requests. Okay. And then for ORAM and 2PC, I guess the state of the art is picogram. This is a paper that will appear in Crypto 2025. We have our the paper is not out yet, but our open source has been out for a long time. And essentially, there are two ways to look at it. If you only care about the critical part, the online response time, it's only about 30 to 40 milliseconds on this data size. But if you also care about like the gobbler time, the offline time, including the gobbling time and the network time, it's about 300 to 600 milliseconds.
This is all for what kind of queries?
This is just every memory. Let's say you make a memory lookup. So
like
for
the same as PIR, just looking up
yes,
C of X.
yes. Actually, for ORAM, we can do even a little bit better. This is actually for key value star, where the address does not need to be contiguous. But for everything else, I'm assuming just memory lookup. Okay. And then PIR is like, this is based on our Piano implementation. And the online computation time is 12 milliseconds. The total time is about 100 milliseconds, but really like most of this is just ping latency. Like this is running on a network with like 60 millisecond ping latency. Even if you send a packet with 0 bytes, it's going to take you 60 milliseconds. Okay, so really like it's just dominated by ping latency.
This is for static data.
Yeah, this is for static. Like for for ORAM and this double RAM, it doesn't really matter. Like you get updates for free. Yeah.
How many queries are you advertising over here?
You mean for PIR or for? How many queries? I don't think it will matter to the. It doesn't matter to the results. I mean, like we have this internal parameter, which is the window size, but like it's kind of in the unbounded setting, right? Like you can, yeah. So I think these numbers, the window size, I mean, of course you have to choose the window size carefully, like to kind of balance the, I mean, I guess in this case, it's just dominated by the network latency, but the trade-off is between the client space and the computation time. Yes.
The ORAM result is the whole database in.
Sorry, the ORAM is what?
The entire database is in memory or stored in disk?
It's like if something is stored on disk, it's like 15 milliseconds. If everything is in memory, it's 20, sorry, not milliseconds, microseconds. If there's some stuff on disk, it's about 15 microseconds. If everything's in RAM, it's about 20 microseconds. That's why there's a range. Also, I want to thank my students for the amazing work. Okay. So I want to, like, before I talk about our construction, I want to first answer a basic question. Why don't we just do a linear scan? So when I teach like undergrad algorithms, if I tell my students, oh, here's a log n algorithm and here's a linear algorithm, and no one's going to question why we should use the linear algorithm. But when I talk to practitioners and theoretical cryptographers, the question I get is like, why don't we just do a linear scan? It's kind of interesting, like practitioners and theoretical cryptographers, they come with very different mindsets and motivation, but they're asking the same question. Okay, so let me give you some perspective why we don't want a linear scan in practice. So today's signal is running ORAM plus TE. They need 6 servers to handle the load. So by the way, their implementation is about 20x slower than ours. So it's possible if they switch to our implementation, it would just be 1 server. So back in 2017, they thought a linear scan was going to do better. So they had a linear scan implementation, and it's an extremely optimized linear scan. Like they do some batching and stuff, and they needed 500 servers to handle the load. This is linear scan without crypto. It's like linear scan inside the TE. And then they also initially, as I said, Tal asked the question, why do we need TE? Like they tried to do it without TE initially. So they looked at these classical PIR implementations, and they did like some kind of estimate. It would cost them about 300 million USD per year. So it's just not viable. So by the way, this number, I think, could be a little bit outdated. This number was estimated in 2023. So it's possible Henry will have a better number. But even if it's like, let's say 100 times better, it's still like 3 million USD per year. And I also want to mention, like, the bottleneck may not be the latency. Like for something like PIR, it's trivially parallelizable. Like if you have many, many computers and cores, you can just parallelize the latency away. But it's not going to parallelize this your build away. Okay, so in today's talk, I'm going to tell you 2 extremely simple constructions, an ORAM construction and a PIR construction. So simplicity goes a long way in practice. You don't need any crypto background to understand these constructions. And so let's start with ORAM. Okay, so I want to first talk a little bit about how we got here. I mean, of course, at the very beginning of time, we had the first ORAM construction by Goldrick and Ostrovsky. It follows an algorithmic paradigm called the hierarchical ORAM paradigm. These schemes can get log cubed cost per query, and they also prove a lower bound that any ORAM scheme must incur at least logarithmic cost. So n is the database size. So this hierarchical ORAM is like complex, and they have huge constants. And then I guess around the last Simons, 2011 to 2015, there was like a paradigm shift. We came up with a new class of constructions called tree-based ORAMs. And with tree-based ORAMs, we could shave 1 log factor. So it's like log n squared in theory. But actually, these 2 log n's are not equal. Like one is actually a log base 2n, and the other is log base, a large base n. And that log n is just like 2 or 3 in practice. So really, in practice, we are seeing logarithmic performance. And for today's talk, I'm actually going to tell you how tree-based ORAMs work. You'll see like they're just extremely simple data structures. There's no crypto involved. Okay, so are you ready for the ORAM? Any questions?
Maybe one. So this paper following yours, this ORAM and PIR, they still theoretical, or they?
So there was this paper, Futurama, and they claim to make it practical. Can you ask the question when I actually talk about practical? Like I think there are many, so they have some implementation, but number one, once you see our performance numbers in comparison with the prior work, you'll see like how practice differs from theory. Okay. So in order to construct ORAM, let's first try to gain some intuition, right? So the most naive idea is we are going to permute all the blocks in memory. So I will assume block is the atomic unit of access. And I'm going to assume everything is encrypted, and the only thing the server can observe is the access pattern. Oh, I guess like I sometimes use the word memory and server interchangeably. Basically, the adversary can only observe the access patterns. So if we permute everything in memory, like let's say I want to access logical address 9, right? I would just go to a random location. So it seems like it doesn't leak anything. But if you think about it more carefully, there's a problem because just permuting everything gives you only one-time security. Like if you guarantee every block is going to be accessed only once, then it's fine. But once you start visiting the same thing, more than once, let's say in this scenario, I have 2 accesses to the same block, then the server or the memory can observe the frequency information. Like it can gather statistics, and then it can do a statistical inference attack. So this strawman solution is insecure for the same reason why deterministic encryption is not secure, because you can gather statistical information.
Who knows where the permutation is? Even for one time.
Oh yeah, I'm assuming, let's say the CPU, the client knows, the ORAM client knows the permutation, but let's say the adversary doesn't know. So if it's like everything is accessed only one time, you just see like every access goes to a random location.
But
and
then you might as well hold the whole data rather than holding a permutation, no?
If you start them in known locations, then let's say Signal can see, Shafi, Tao is Shafi's friend. But if the server doesn't know which record is Tao's record, then it doesn't really matter.
No, I understand the security. What I don't understand is who is holding a random permutation is the same as just holding everything, no?
Pseudo-random, yeah.
So I see. So,
You're worried about the space.
yeah, I just didn't understand where the permutation.
Let's assume it's pseudo-random. It can be generated with a small key. But it's like this is not our solution in the end anyway.
Yeah,
so
no, I
really
understand. Okay, got it.
So the key insight to gain from this is like the blocks have to move around. Because if everything always stays in the same place, then you end up leaking the statistical information, right? Once you access the same block multiple times, you leak frequency and you also leak things like co-occurrence. So we'll keep this intuition in mind as we go over the scheme. And in fact, it has to be the case every time you access a block, you have to relocate it immediately. You cannot wait. Okay, so let's see how the scheme works. We are going to use a tree. It's a binary tree, and every node is called a bucket. By the way, during the last assignments 10 years ago when I gave this talk, there was an important question on this slide that caused a lot of commotion. The question is the tree upside down? Okay. So every bucket is going to have like a finite number of slots, and every slot can store either a real block or a filler block. So a real block is encryption of actual data, and filler block is just encryption of 0. It's only there for security. Okay. And the main invariant we want to maintain is every block is mapped to some random path. So in this case, the block with logical address X is mapped to the blue path. And I'm going to cheat a little bit and assume the CPU is asked to store a position map, and the position map records where every block is. So going back to Tao's question, this position map is very large. That's bad. We'll get rid of it in the end. Okay, so for now, I'm just going to cheat and assume the CPU can store it. So now reading the block is very simple, right? Because all I have to do is I need to find out which path my block resides on, and I'm going to go and visit that path. In this case, I will go visit the blue path, and I'm guaranteed to find the block X. So if what actually happens is like if the block is what I want, I will remove it, hold it in my hand, and encrypt 0 and write it back. If it is not what I want, I'm just going to take what I read, just encrypt it, re-encrypt it, and then write it back. And because the encryption scheme is randomized, the server cannot tell from which slot you have removed the block. Okay, so reading is very simple. And at this moment, we have to recall our key insight. Now we have read this block. We have to relocate it immediately. Okay, so how do we relocate it? We need to write it somewhere else. The most natural idea is I'm going to pick a new random path, let's say the green path, and I want to write it to the green path. And to do that, of course, I have to update my position map to reflect that it is now on the green path. But the real question here is like, where on the green path can I write the block? Like, for instance, can I write it to the leaf node? Can I write it to the leaf node? Okay, I see many people saying no, right? So the answer should be no, because if you write it to the leaf node, you leak that you have read something from the blue path, and it's now on the green path. So the next time, if you are asking for the same block, it'll leak information. Like if you go to the green path, it's likely you're just asking for the same thing. Okay, and for the same reason, you should not write it to any of the internal nodes, because all these internal nodes will leak partial information about the choice of the path. And the only safe place to write it is into the root. So we are going to write the block into the root. And this is secure because it doesn't disclose any information about the choice of the new path. If we do this, okay, I need to resolve the issue, like we cannot keep writing things to the root, but just take a moment. Like if we are doing this, the key observation is that with every request, we are going to visit a random path whose choice has not been disclosed before. So that's why the scheme is secure. Okay, and basically to make the scheme work, the only issue we have to resolve is like we cannot keep writing things to the root because it will soon overflow. So how do we deal with that? We are going to introduce an eviction process. And how does eviction work? I'm going to tell you the eviction algorithm of path ORAM, which is the ORAM that Signal implemented. So in path ORAM, the idea for eviction is, when I want to fetch some block, I'm going to go to a random path. Since I'm already fetching this entire path back, I might as well do some work and perform eviction on this read path. And the way we perform eviction is kind of like the most aggressive eviction possible. We are going to take all the blocks on this path, and we are going to pack them as close to the leaf as possible. But importantly, this has to be done subject to the path invariant. Like it may not be possible to like take an arbitrary block and write it to the leaf because that's not the path where the block wants to be. Okay, so if you do this, now you think about the scheme, right? What happens is every time you want to request some block, you are just requesting a random path, and that's it. So that's why it's called path ORAM, because every request just goes to a single random path. And to prove that the scheme actually works, we have to prove that with this eviction process, there's not going to be overflow, except with negligible probability. And indeed, we show that if the root size is super logarithmic, the root bucket, and every other bucket is constant size, then we can prove that except with negligible probability, no bucket will ever overflow. The proof is sophisticated. I will not try to cover the proof in this talk, but I think it's fortunate that the proof was sophisticated, because otherwise reviewer B would have said, your paper is trivial, and rejected it. Okay. Oh, there's only one last thing. I promised Tal we are going to remove the position map. And this problem can be solved with one word, that is recursion. So we are going to take the position map, recurse, start the position map in a smaller ORAM. And we recurse until you have a constant size position map. And at this point, you can just start on the client side. Essentially, if your block size is like some constant times log n, then every time you can think about your position map, it should be a constant factor smaller than the original database. So every time you can shave at least a constant factor, and the recursion will end after logarithmic depths. So if you account for the total cost, it's log squared. One log comes from the height of the tree, and the other log comes from the depth of the recursion. And I want to emphasize the depth of the recursion. That log actually has a large base, because in practice, the block size, like for instance, for SGX, it's 4 KB, and the recursion is usually 2 or 3. The recursion depth is just 2 or 3 in practice. So really, in practice, this scheme behaves like a single log n performance. Okay, so that's path ORAM. It's extremely simple. It's a tree. This is the entire pseudocode. It's 16 lines, including and for and if. It's so simple you can print it on a T-shirt. Okay, practical considerations. Maybe it'll come close to answering Yevgeny's question. So when you take the scheme and you implement it in practice, you don't want to just take the scheme on paper and directly implement it. And there are many reasons why that's true. And here's an important reason. So when we write papers, or when we teach actually undergrad algorithms, we work implicitly in the so-called word RAM model. And in the word RAM model, the CPU is going to interact with some memory. And with every instruction, you are going to make a memory access. And every time you can access, let's say, 1 byte. And in this model, the memory I/O cost is the same as the compute cost. However, in practice, if you are implementing this for trusted hardware, you have some enclave, and the enclave, there's the enclave's memory is limited, and your database is often much bigger than the enclave's protected memory. So whenever the enclave needs to read an encrypted page from outside the enclave, no matter whether it resides in RAM or on disk, it has to perform a heavyweight operation called the page swap. And the page swap is typically on a 4 KB basis. And this page swap is pretty expensive. And one thing to note is that even if you only want to fetch 1 byte from, let's say, outside the enclave, you have to fetch 4 KB. It doesn't make sense for you to fetch just 1 byte because of the overhead. And this page swap is expensive because you need to make system calls, you need to encrypt and decrypt. And possibly if the data is residing on disk, you also have to make a disk swap. So this model, actually, in algorithms literature, it has been studied for a long time. It's called external memory model. So really, you want to take path ORAM algorithm and adapt it to the external memory model. If you don't do that, you'll discover with your implementation, like I can give you some example, like for instance, Oblivious. If you just take path ORAM, implement as is, most of the cost is going to be on the page swap. And that's why it's so expensive. But if you do these external memory algorithmic tricks, you can get, so the key is you can get asymptotically better performance in this external memory model, in terms of number of page swaps. So that's why if you look at our implementation, it outperforms Oblivious by 15kx, which should be pretty surprising because we are just talking about a tree data structure. And if I ask you a priori, I'm writing a paper on the tree data structure, what is the percentage I can improve over the previous paper? It should be 10%, right? But it's there's stuff you can do to improve the actual performance on real world architectures. So we are faster by 20x than Signal and by 100x in comparison with Meta. Okay, and I also want to mention, actually, our implementation is not using path ORAM. We are using circuit ORAM because when you can make the page swap really cheap, the computation actually becomes more dominant. And circuit ORAM is a variant of path ORAM that minimizes the computation. So we are actually at a point where the computation actually really matters because we have got rid of the heavy page swap overhead. Okay. So another thing we need to keep in mind in practice is oftentimes you may not need a generic ORAM. Oftentimes if you have specific algorithms, specific data structures, let's say graph algorithms, page rank, lots of it is a matrix factorization. a lot of these algorithms don't need generic ORAM, like because they can either be efficiently expressed as a parallel algorithm, or they, it's some kind of data structure, or it can be expressed efficiently in some computation model. And algorithms in these computation models can be made oblivious much more efficiently than generic ORAM. Specifically, in the algorithms literature, there is a different MPC. It's called the massively parallel computation model. And this characterizes things like MapReduce and Spark. This is like the de facto computation model like Google and Facebook use, right? If your computation is amenable to be expressed in this massively parallel computation framework, you can get obliviousness with constant overhead. It's a very small constant. You don't need ORAM. So like in practice, I think you should always keep these things in mind and see whether you actually need a generic ORAM or not. So in ongoing work, we are trying to build oblivious STL. And you can think of it as like a oblivious counterpart of like C++ STL. So to make these customized oblivious algorithms more available to people. Here's another large-scale application of ORAM. In Pittsburgh, if you go to the coffee shops, you can buy something called ORAM's Cake Donuts. If you come to Pittsburgh and visit me, I will treat you to ORAM, and you'll crank out some theorems for me. OK, so PIR. I'm going to tell you a very simple PIR scheme called Piano. But before that, let's look at some strawman, and let's look at how things have evolved to where we are. So the most straightforward idea is to use FHE. And the user will encrypt her query using FHE, and the server will homomorphically evaluate the answer and send back the encryption of the answer to the user, and the user will decrypt it using her secret key. So this solution has very nice bandwidth. It's like constant or polylogarithmic bandwidth. But the server computation is really large. The server has to do a homomorphic evaluation. And in the circuit that's being evaluated, the database has to be encoded in that circuit. So that evaluation is at least linear. So in fact, this class of scheme is called classical PIR. Classical PIR was first invented by Core et al. In 1995. And since then, there has been a long line of literature that primarily did two things. Like one is to build classical PIR from various assumptions. So we can get this result from various public key assumptions. And then the second line of work is like spiral simple PIR, where we really try to optimize classical PIR and get the maximum performance out of it. I tried to find the actual deployment of classical PIR, and I found one with Henry's help. So Henry said he talked to Kevin Yeo from Google, and they're actually running a small-scale application. Like they're using classical PIR to privately fetch device unique config. Like whenever you register a new device, it's going to fetch some device configuration from some small database. But as you can see, like in this case, the database should be pretty small. And that's why this linear cost doesn't matter. And for the applications I have mentioned, like Signal, blockchain, the database is really large. Like for Signal, we got a synthetic database from them. It's like 100 million to 200 million users. In their blog, they say they're aiming for 1 billion user. So for them, this linear cost is just really going to hit. So therefore, in order to overcome this linear barrier, Bimo, Ishai, and Malkin introduced a new model. It's called the server preprocessing model. And there has also been a line of work on the server preprocessing model. And the latest result is by Lin, Mook, and Wicks. It's in a groundbreaking paper that won the Stock Best Paper Award. And they show, like, assuming ring LWE, you can get essentially polylog bandwidth and polylog computation per query. But assuming the server is going to consume n to the 1 plus epsilon space. And the idea is like they're going to take the database and encode it into some, you can imagine some kind of locally decodable code. And then they use crypto to make the queries to make the locations query private. Okay. So So this result is very important because it sets up like a dream, right? Because this is, if you look at this performance, it's kind of like theoretically dream. But when you look at the scheme, they have astronomical constants. So this is very, very, very far from practical. And so one question we asked is like, is there a way to get a truly practical PIR with actually sublinear computation? So this is what I want to talk about. And I will talk about a scheme called Piano, which is in the so-called Klein preprocessing model. And the Klein preprocessing model was first, I think it was proposed in like 2 papers, one by Patel et al. And the other by Henry and Dima. And I think the Henry's paper is cited more often because they were able to get the sublinear computation, whereas in Patel et al., they still have linear computation, even with the Klein preprocessing. Okay, so Piano is in this Klein preprocessing model. And I'll explain the scheme and you'll see what Klein preprocessing is. The result we can get is like we have an extremely simple Klein preprocessing PIR, and the cost is just basically square root n. Square root n compute, square root n bandwidth. The client needs to have roughly square root n space. And one thing that's very cool is all we need is PRF. We don't need any fancy crypto. And this also is maybe a little bit surprising at first sight because there's this elegant impossibility result, CMO. And they showed that if you want to have a non-trivial classical PIR, you have to have public key crypto. Okay, but it turns out in the Klein preprocessing model, we can overcome this barrier. And I also want to mention like these asymptotics, the compute and bandwidth costs are actually almost optimal subject to these constraints. So basically, if you assume the server stores only the original database, the client is subject to square root n space, and we only use minicrypt, then these performance numbers are asymptotically optimal. So how does the scheme work? First, there's going to be a pre-processing phase, and you'll see why it's called client-side pre-processing. Okay, so the idea is we are going to take this database, divide it into square root n size chunks. So there's going to be square root n chunks. And we are going to sample one random index from every chunk. So this gives a set of indices. We are going to write down the set. And we are going to try to go to the server and compute the parity of the database at these selected indices. Okay, so this becomes the first entry in my hint. And we're just going to repeat this. We're going to pick a second set at random, compute the parity of those indices, and so on and so forth. And then we are going to repeat this roughly square root n times. So this creates a hint table with square root entries. But besides this, we are also going to record some replacement entries during the pre-processing. So what are replacement entries? Essentially, for every chunk, I'm just going to sample polylog entries at random, and I'm going to remember what the database values are at those polylog n locations. Okay, so this whole thing becomes my hint. And this hint will help the client during the online query phase. So this is why it's called client-side preprocessing, because the client is going to end up with the hint at the end of the preprocessing stage. So far I've described what the client, yes, Syria.
Isn't this n space, am I missing something? Are like the subsets chosen like pseudo randomly or?
You're ahead of me. Yes, so this is like n space, because every set is square root n size. We have square root n sets, so that's not too great. And it can be compressed using a PRF. So essentially, you are going to generate the set using a PRF key. And if you do that, you just end up with roughly square root n space. And this is the only place where we use PRF. It's just to compress the client space. Okay.
So one more question. So that means you're just sampling independently, like subsets could have overlap.
Yeah, they will overlap. We actually want some kind of overlap for it to work. Okay, So for the rest of the talk, I'm going to assume the sets are stored in the clear just for convenience, but in practice, we use the PRFT. Okay. So I want to mention like this preprocessing, how do we actually do the preprocessing, right? So this is the state we want to end up with at the end of the preprocessing, but actually the preprocessing can be done with a single streaming pass. So let's say during some subscription phase, the client is going to make a single streaming pass over the entire database, and it can write down all these hints at the end. The cost of this can be amortized over unbounded number of queries. Okay, and also importantly, the client only needs square root and space during this whole streaming pass. That's why it's called a streaming algorithm.
Do I need to have some kind of reverse lookup, given a location, find the set, or all the sets contained in this?
Not really. I'm just going to every time fetch like square root and next block from the server and like update the parity. You can. It's not hard to show the streaming pass. It's going to take linear communication and like linear computation. I mean, ignoring log factors. Okay. So this is the preprocessing, and now let's go to the query phase. So suppose the client wants to retrieve index 5. So how do we handle this request? First, the client is going to look up its hint table, and it will find some set that contains the query. So in this case, the second set contains the query, and I'm happy with it. And then I'm going to go to these replacement entries, and I want to find a replacement entry whose chunk is the same as the query. Just find some replacement entry in the same chunk. And now I will take the set that I have found, but I don't want to disclose my query to the server. So what I will do is I will take the spot that is my query. I will replace it with this random index in the replacement entry. So I will send this modified set to the server, and the server computes the parity of the set and send it back to me. And I can reconstruct the database at index 5 by computing the simple XOR. In particular, these two values come from my hint, and this is the server's response. So correctness can be checked fairly easily. And the question is like, why is the scheme secure? If you think about it, if you pick a random set subject to containing your query, and then you rewrite your query with some random index, then this set is the same distribution as a randomly sampled set. So essentially, when you submit a query to the server is just going to see a random set that doesn't contain any information about your query. So this is very nice, but on second thought, actually, maybe we should not be too hasty to conclude. Like, actually, this scheme is only secure for one query. And why is this the case? Yes.
You're not rewriting any entries in the database after you read.
Yeah, that's exactly the point. Because like once we consume an entry, right, it's like we cannot reuse it again. If we reuse it, of course, it's going to leak information. But if we just delete it, it's also not okay. Because if we delete it, then the remaining sets are less likely going to contain my query 5. So this skews the distribution of the hint table. So whenever you make future queries, it'll have a little bit of bias. How do we fix this issue? I'll tell you like the simplest way to fix this issue, but incurring a log factor. But in our paper, we can get rid of this extra factor. So the simplest way to fix this issue is basically once I've consumed this entry, I'm going to replace it with a fresh entry. But this fresh set has to be sampled at random, subject to containing the current query 5. Because if you think about it, the entry I've consumed is a random entry subject to containing 5. So if I replace it with another random entry subject to containing 5, the whole hint table is still just like uniform random hints. But the only problem is like for this new set, I don't have the correct parity. So now this line becomes broken. So this is a broken hint. And it turns out this broken hint doesn't matter because it's going to, like, next time if you happen to consume a broken hint, you'll encounter a correctness error. But the correctness error happens only with a constant probability. So all you need to do is to parallel repeat the scheme logarithmically many times super logarithmically many times to get negligibly small correctness failure. This replication overhead can be avoided if you just add a couple more tricks. But I won't go into details.
So just to make sure I understand, you fix security by herding correctness, and then you amplified correctness, so correctness will be good.
Yes, yes, and like I guess the client knows whether, because the client knows whether the answer is going to be correct or not. So if you just repeat super logarithmically many times, you can fix it. Yes.
So this protocol requires the client to be stateful, right?
Yes,
Okay.
that's why it's called the client preprocessing model. Like the client is stateful. So actually, in the initial paper by Patel et al., they call it client stateful something PIR. It has a different name.
But in general, in the client preprocessing model, the client does not need to be stateful. We can have scenarios where the client for each query just needs to rely on the initial preprocessed data.
Yeah, maybe you have a different model in mind, and we can take it offline. Yes.
So if you're consuming these hints, do you have a bound on the number of queries you can do?
Yes, that's on the next slide. Oh, next slide. Okay, let me summarize the scheme so far, and I'll answer your question. So the scheme so far is like, it's basically very simple. There's a pre-processing phase in which the client makes the streaming pass, consuming square root n local space. At the end of the pre-processing phase, it has a square root n size hint. The pre-processing takes like linear time. During every online query, the client is going to send a square root n size set to the server, and the server returns the parity, and that's the whole protocol. It's extremely simple. The only problem is, like, I haven't talked about how many queries this can support yet. And in fact, if you think about it, you can only support square root n queries. And why is this the case? So we have downloaded polylog replacement entries for every chunk. Once we run out of the replacement entries, we're done, right? So let's imagine the database is randomly permuted. And in this case, you can imagine every query is random because the database, using the randomness of the permutation, every query is random. And we can also assume all the queries are distinct because the client has square root n space anyway. It can cache the answers of the most recent square root n queries. So assuming all the queries are distinct is without loss of generality. And now, if I have window size of square root n, it's like throwing square root n balls into square root n bins, where the bins are the chunks. And with all but negligible probability, you are only going to consume like super logarithmically many replacement entries from every chunk. So the replacement entries are sufficient to support this many queries. So how can we make it support more queries? It's just through an extremely simple idea called pipelining. Like, we are going to run this initial preprocessing once, and then the next preprocessing will be piggybacked over this window of like square root n queries. And you can amortize this preprocessing over square root n window, and it only incurs square root n cost. Okay, so that's Piano. We implemented it. So for this evaluation, we used the 100 gigabyte database. It has 1.6 billion records. And the setup we have is like, it has 60 millisecond ping latency. So you can see like the actual computation only takes 12 milliseconds, but the response time is 72 milliseconds because the ping latency dominates. Like the compute is so small, it doesn't even matter. Like the ping dominates. And there's a little bit of bandwidth cost, but it's not significant. In comparison with simple PIR, I think this is the practical state of the art for classical PIR. Our computation is almost 3 orders of magnitude better. The end-to-end performance is 150x better. That's because it's diluted by the pin latency. Okay. So I want to talk about some open questions and then end my talk. I will mostly be asking open questions for 2 and 3, the RAM model, MPC, and PIR. But I guess I realize I haven't talked about RAM model, MPC yet. So I'm going to give you a little bit historical perspective. In 2012, in this multi-author paper, they proposed RAM model 2PC. And then, so this RAM model 2PC, if you have a computation that runs in T time, you'll need to have T log n number of interactions. So it's like very chatty, very interactive. And Gobble RAM is the same thing, except that the number of rounds is only 2. And then in practical land, so this is last Simons. When we were in the last Simons, you know, we are basically at the point where we can make RAM model 2PC practical. And the approach is to use circuit ORAM on top of either Gobble circuit or something like speeds, some practical MPC backend. And how to make Gobble RAM practical has been open for a long time, but I think very recently there has been a lot of progress on making Gobbled RAM practical. And essentially, the comparison is like we are taking this, but compressing this T log n rounds to just 2 rounds. And this, right now, this can be done without actually compromising. Actually, I should say it this way, like Gobble RAM is actually now faster than the previous state of the art from 10 years ago. Maybe back to Yevgeny's question. So here's I guess like, I think this is both encouraging, but also a little bit disappointing. It's encouraging in the sense that we have, come pretty far since 10 years ago. But on the other hand, in comparison with ZK, like when we are writing these papers, like I was trying to find a practical state of the art to compare with. And then I realized the practical state of the art was my own paper 10 years ago. Okay. So this is like Gobbled RAM, but if you care about the theory, like you can, like Gobbled RAM, the communication is not succinct. You can make it succinct, and this was proposed in several concurrent works around 2015. And then this is the work I talked about, which enabled RAM model FHE, and that's fairly recent. Okay, open questions. So if you think about the practical land and theory land, like in practical land, we have schemes that are built from lightweight assumptions like one-way function and decisional Diffie-Hellman. They're not succinct, like the bandwidth is still proportional to the computation time of the program. In theory, we can do better if we have I/O or ring LWE. The bandwidth can be made polylog. So ideally, it would be nice if we have like a scheme with this asymptotics that's practical. I mean, I guess it depends on how you look at it, because in practice, really the end-to-end performance matters. So this also kind of makes sense, because if you look at the bottleneck complexity, which is the maximum of the two, like if you only care about bottleneck complexity, then this is already fine. So the question is like, what's in between? This is like a bigger question, but you can break it down into a lot of smaller questions and natural next steps. And in fact, all the questions Elaine and Peter asked about circuits, you can ask the same for RAM, but except that I think fewer people have looked at RAM. And one reason why I think this is like still not practical yet is I think we need more progress on the RAM side, because all these large scale applications people care about, they really need RAM. Okay. PIR open questions. So Yevgeny asked why PIR, what are the challenges in actual application? Like one challenge is the update issue that you mentioned, like the piano scheme I talked about is in the client pre-processing model, and every update will have to involve the client, which is a little bit tricky if the updates are much more frequent than the queries. But if the updates are about as frequent or less frequent than the queries, then maybe it's fine. You can just piggyback the work when you make the next query. There are also actually big advantages of using like this kind of scheme because they support general computation. Like in a scenario where your application logic may change a lot, and I think in a lot of these practical applications, it is like software updates do happen, and I think anything that supports general computation has a big advantage. Like I think this PIR, we haven't gone very far. Like we have tried to do a little bit more than just simple like query. Like there's a paper by Henry on like nearest neighbor search. I mean, we also have a paper on that, but it's not too much more than just simple retrieval. So PIR open questions like, can we make the scheme, have a practical scheme for fast evolving database? And maybe one way to try to get a scheme is to look at server-side preprocessing, because actually server-side preprocessing is more friendly to updates. Like you can use the standard hierarchical data structure and updates will not involve the client. Whereas for a client preprocessing scheme, even if you use hierarchical data structure, it will still involve the client. I mean, of course, the ultimate dream, can we have practical RAM model FHE? I mean, again, these are pretty high level. You can break them down into lots of more finer grained questions, and I'm not going to try to do that because I think Elaine and Peter already asked a lot of like low level questions. So I want to conclude by saying where we were in the last assignments, where we are this assignment, and where we want to be in 2035 in the next assignments. If you look at the way things evolved, okay, the previous assignments, like we were having a paradigm shift for ORAM, right? We were going from hierarchical ORAM to tree-based ORAM, which was like important for the practicality of ORAM. And this time ORAM is really, deployed in real life at a large scale. I would like to think that, right now we are at the same kind of theory to practice juncture for doubled RAM and preprocessing PIR. So perhaps one thing we can ask is like, next assignments, we want to see large scale deployment of these. And as for ORAM, I think the theory is quite mature. And for a lot of these computations, we are just trying to I think the lower bound and the upper bound are tied up to constant factors, but there are still actually a lot of challenges to practical deployment. Like for one thing, the reason why Signal went for a linear scan scheme is a good sign that we don't have too much like open source tool chains, like libraries to support this kind of development. Or if you are more aggressive, you can also hope in the next assignments, there will be no more TE. Like these will be practical, so we don't need to even worry about TE anymore. Okay. Okay, if you want to be practical, like there are a few things that cannot be ignored, and these are things beyond cryptography. Like one is programming language. Justin mentioned formal verification yesterday, but I also want to mention there's also a lot of work that can be done on the language design, on how to design optimizing compiler, and how to use type system and information flow. Importantly, I want to emphasize that we actually want to catch a lot of potential bugs at compile time using type system and information flow rather than deferring everything to a posterior formal verification, because this will make things much more scalable and viable in practice. Crypto meets algorithms is another big elephant in the room. And I think there are two kinds of questions in this space. Like one is, how can we take crypto and make it efficient on real world architectures? Like for instance, I gave an example today for ORAM, right? Even though ORAM is just a simple data structure, if we use these external memory algorithms that came out of the algorithms literature, we can get like 15,000x improvement, which is very surprising for something so simple. So I think there's a lot of opportunities, like, in the algorithms literature, there's like a lot of interesting algorithms for how to compute things faster on like massively parallel computation frameworks and so on and so forth. The second big question is like, crypto has its own computation model. Like, we are talking about circuits, R1CS, a branching program, RMS, and every crypto scheme has a different implicit computation model. And a lot of the times, like, we have a good understanding what can be computed in polynomial time in these models, but I think we want a finer grain understanding of how fast it is actually to compute various important tasks in these crypto models of computation. Okay, thank you so much.
So for the preprocessing, client-side preprocessing PIR, are there any works which avoid the initial database to define?
There's server-side preprocessing, like Limok Wix doesn't need that.
I mean specifically within the client-side preprocessing, like you.
So there is, I think, like Henry's has like, you know, this framework was, as I said, was like initially proposed by Henry and Dima. And they had some initial schemes, but some of them don't support unbounded number of queries. And then there's like another class of schemes. So you can, we have these papers where we can get like polylog bandwidth, but it's cheating a little bit because the server still kind of has per client state. So
I think I would say it differently. I would say that if you have two servers, you can eliminate this streaming of the database and you get all the same costs. One server done, it's kind of inherent.
Yeah, that's also a good way to, if you have two servers, then that can be a good, I guess like it's also not too clear. So for two server, there's the gobble RAM solution and there's also two server PIR. The two server PIR is asymptotically worse because the compute, I think, is square root n. The gobbled RAM is like, so by the way, the gobbled RAM is kind of optimal. Like if your block size is big enough, it has a single log n. And I think, yeah, I guess it's not clear which of these solutions will become more practical. Like gobbled RAM has the advantage that it supports generic secure computation, whereas I think for PIR, we're still kind of in retrieval only mode. So yeah, so both are worth looking at. And I guess maybe in today's talk, I focus more on gobble RAM because of these. I think it's more like an explicit choice to focus more on gobble RAM.
Have people worked on practical symmetric PIR, like to protect the data?
And there's a generic transformation that uses an Oblivious PRF to get it. I think like
it's not. Is it very practical?
Yeah, I think. No? I think like I talked to Kevin Louis. Like he is also developing these ORAM algorithms for Facebook. He said he has some efficient implementation of Oblivious PRF, and I haven't tried to.
Signal doesn't care if Shafi learns the names of other users of the system.
Right now, they don't. Yeah.
Is there a reason why? Is it because it's the trusted hardware that's really learning and not Shafi? Is that why they don't care? Because it seems to me like an obvious problem with privacy, no?
Yeah, that's a good question. I mean, I can ask them if this is important to them. Because I guess like the thing is right now, unless you have authenticated inputs, right? Because otherwise, how do you check? Like if you claim Henry is your friend, how can Signal check whether Henry is really your friend or not? Like, maybe if you have like some authenticated inputs, like some kind of, I'm visiting this company called 0x Park right now, and they are developing some kind of ZK application to, you can have like social reputation with ZK. Like if you have these kind of things, then yes, I can send a query to Signal and prove to Signal that Henry is indeed my friend to fetch Henry's record.
Thanks.
Thanks, Elaine, again.